Hello everyone. This is Mohamed ElGawady. I am a professor structural engineering in Missouri University of Science and Technology. I'm going to talk today about shear strengths of hollow core fiber concrete steel columns. My co-authors and my student Mohamed Abdelaziz. This is part of his PhD work. So I'm going to give first an introduction about the topic. This has been going on for a while now, our research on this area. So we are looking for having a prefabricated substructure. And one of the options for a prefabricated substructure is to have lightweight elements, and in particular hollow core columns. So what we are proposing here is to use three different materials: fiber reinforced polymer tubes, and then steel tubes, and then the two tubes sandwiched a concrete shell. So you have the concrete shell sandwiched between the two tubes: steel, the inner steel, the red one over there, the inner steel, and the outer fiber reinforced polymer tube. So this is just a schematic of the how things looks like. It's not the right scale; it's the distorted scale, just for illustration only. So steel inside, concrete, and then the tube, the fiber tube. So what is the advantage? Well, because of the hollow tube, you can cut up to 75% less concrete material. Of course, you would get lower weight and lower construction time. So, for example, over here, this is our reference column with the reinforced concrete columns, the spirals over there. So it took from my student about 2 weeks to do the fabrication of the columns. The other one that we propose, the two tubes act as a stay-in-place formwork. So you just fill in between. So it's literally a few hours just to fix the two tubes in place and then fill in between with concrete. So you cut a few weeks to a few hours. Here's just a steel tube fixed on the cage during the construction. As I mentioned, those would be stay-in-place formwork. So if you are adapting the cast in place, we have the steel pile, the steel tube inside, and then you have the glass fiber outside, and then we fill in between the two pipes with the concrete. Concrete cannot escape anywhere. Concrete has a full confinement from inside with the steel pipe, from outside with the fiber reinforced polymer tube. You get a continuous flexure and shear reinforcement by the steel tube. Higher durability. So as I mentioned, for construction, you can have two different options: either cast in place, as we see over there. We have the steel pipe engaged in or embedded in the footing, and then you add the glass fiber tube, and then you fill in between with concrete. The other option is to go for a full precast. So for the precast, the connection would be through a steel, the steel pipe itself. So the FRP from the top and bottom will be terminated, and then the connection would be a very simple male-female connection through the extension of the steel pipe. So here in the lab, we have the concrete footing, we have the opening on the, we have the recess on the footing where we're going to insert the steel pipe. So now this is the full precast column. We are inserting, as you see over there, the steel pipe on the bottom. And now we are inserting the steel pipe into the concrete, and then we grout the area between the steel pipe and the footing. This is one of the columns during testing. So the column are fixed to strong footing. The footing is the lab strong floor, and then we apply the axial load using the two pumps over there. Those two pumps are working to keep the axial load constant during testing, and the column head over there are connected laterally to two actuators that apply the force back and forth, 2 cycles at each displacement level. And here is just a video for testing. And on this particular test, we actually went up to 13% drift. And this is, we inserted some camera inside the columns. So this is display the elastic buckling into the tube. So you would see here compression and buckling of the tube. And then once you remove or you reverse the load, the steel go up again and stretch back. And we achieve different modes of failure. This is for the reference reinforced concrete column. This was well-designed reinforced concrete column. So as you would expect, you get the spalling and some buckling, fracture of the rebar. And those are the hollow core columns, the new ones. The reference column was a solid column as well. So the other columns were hollow core columns. And as you see, some of the columns we achieve fiber rupture. So you can see the fiber over there at the fiber, the filament angle, the 45-degree angle. Some other, we get a rupture on the footing. We did not have enough development length. And then also we get rupture on the steel pipe on some of the other columns. So we have a well-designed to the extent that we yielded the steel pipe, the steel tube. Again, here is just a flavor of the results. So this is a mount versus a lateral drift. So the one far left over there is the reinforced concrete column, the well-designed. So it's well-designed, so really no surprise. It behaves very well. You get elastic and then you're still yielded. So you go like horizontal plastic and very wide loops indicating a well energy dissipation. The second one, the one in the top middle is also behave very much similar to the reinforced concrete one, but with a higher strength. The higher strength can be adapted using whatever, can you change by using the whatever tube thickness to achieve the required mount. And then the one far right is one of the specimens where we use a very thin FRP tube. And because we just change the FRP tube, we achieve the same strength as the one in the middle, but it was very braided because we do not have enough confinement. And then the one on the bottom left, we did not provide enough development length. So you have an embedment issue. And this is why we have a benching and slippage on the hysteretic loop. And then the fourth one, we have a higher steel thickness. So we see a little bit higher strength. And one of the crucial issue for something like this is, okay, how much is the development length or how much is the embedment length to provide full strength? So we carried out some finite element. We did also some analytical work, and we came up with the finite element here is the red one, and the blue one is the equation that we proposed over there. And on the horizontal axis, you have the diameter, the thickness, and the F ultimate of the steel. And then on the vertical axis, you have the required development length. And this required development length is capable of yielding and fracture the fracture the steel pipe. So here is one of the columns where we provided not the required embedment length. So we know before we start, this one would design to have embedment failure. So as you would expect over here, you know, a typical failure in the column because of the pull out of the steel. And this is very much the same, but we provided enough embedment length. So you would see here the difference. So the red here is embedment length whenever we don't have enough embedment length. Over here, the black one, whenever we provided enough embedment length. So we can tell from, well, the strength did not really increase that much, but it's mainly the energy dissipation with a very fat loop in the case of the black one with the required embedded length. So a next step, as a design engineer, you would like to design the system. So for design, in addition to the development length, you would like to know, okay, how much is the flexure capacity and how much is the shear capacity. So for flexure capacity, we use a very simple mechanics-based, the only one over there. So we have different strips, and then we integrated the strengths all over the cross-section. The only thing that's we need to mention over there, we use a stress-strain model for the concrete that's considered the confinement from the FRP and the steel. So this is probably the only thing that we need to consider here is the confinement, concrete confinement model. And then we developed the finite element models. The finite element models we use for different things, but one of the things is to investigate the shear capacity of the columns. So here is the column is symmetric, so we only modeled half of the column. So we have a vertical plane of symmetry. And for concrete, we use, this is a concrete that's sandwiched between the different pipes. So for the concrete, we used solid elements to model the concrete. And then for the inner steel, it's a shell element. And then the FRP also is another shell element. We use surface-to-surface friction between the different elements. And then this is the footing. So for the footing, also for the concrete on the footing, we used solid elements. So here's the model, and then we apply the vertical load, and then we apply the lateral load. The lateral load was applied in a displacement control. And we run the model quite a few times. Some of those under cyclic load, and some other time are under just a monotonic load, depends on what we'd like to achieve. So for the calibration, process, so here is the calibration, just as an example. So for the blue one is a static, for the reference for one of the specimens, and then the red one is a finite element. So as you would see, the finite element predict quite well the loops and the strengths and the general shape of the hysteretic behavior. Also presenting here, the green one is the analytical model for the flexural strengths that I presented earlier in this presentation. So in addition to looking at the hysteretic performance, we also look at the mode of failure. Was our model correct in predicting the mode of failure? So this is one of the columns where FRP rupture occurred and occurred on the very bottom. So our model showed the wherever we have this red shells, that's indicating a stress concentration, which indicate rupture of the FRP. After we did the calibration, against more than 10 columns. Once we have done the calibration, we start to apply the column for the, we start to use the column for different applications. So one of those was to determine the shear capacity of the columns. So over here, we tested we ran the analysis for 30 columns. So for those 30 columns, we consider, we group them in 6 different groups. And for each group, we consider different test parameters. So for example, on group number 1 over here, group A, we consider the aspect ratio. So the height of the column divided by the diameter, and diameter F, this is the diameter of the fiber. This is the outer diameter. And look at different diameters ranging from 1.6 to 3.6, like the aspect ratio. And then we look at the FRP tube diameter to thickness ratio. We, for group A and B, we kept this at 71. So this is the diameter over the thickness of the FRP. And then for the concrete or thickness for group A and B and C, we kept this at 4 inches or 10 centimeter. And then for the steel tube diameter to thickness ratio, for group 1 or group A, we have diameter over thickness at 64. On group number B, we played with the diameter of the steel and the thickness of the steel. So we changed the D over T for the steel pipe, moving from 32 to 254. If you are working with concrete felt steel tube, you probably know, 64 and, is probably the right range. However, on this one, we just would like to see looking at the wide range of parameters. So we went up to 254 to see what is the effect of using a very thin pipe, which would expect trigger more local buckling, but we'll see. And then the concrete thickness was the same as before. And then, as I mentioned here, the steel tube to diameter was a parameter. In group number C, we looked at the confinement ratio. So we looked at different confinement ratio by changing the thickness of the FRP. So we moved from 0.1 up to 0.4. And then for group number D, we played with the concrete wall thickness. So it ranged from 3 inches to 7 inches. Load level, this is the applied axial load. Over here, we consider bridge columns. So our maximum applied load was 15% of the axial capacity of the column. And then last group, we looked at the F prime C of the column. So the F prime C ranged from 3 KSI up to 11 KSI. Shahri, how I'm doing on time-wise?
Yeah, although our time is like the whole session time is over.
Okay.
At 6, yeah.
Okay. So over here, we look for the shear strengths of the different models. So every group here is a different color. And then we look at the mode of failure. So over here, for example, this is one of the columns. We have shear off. We have flexure shear. We have also some of the cylinder columns with flexure columns. And then we compare the shear strengths of those 30 columns with the shear strengths from literature. So one of the models here that we looked at is Kowalski and Presley that was developed for or consider hollow core sections, which consider the aspect ratio of the column, the effect of the dual action of the reinforcement, and also the ductility ratio. Another one was developed by Cezanne and Molly for solid cross sections. So over here we have a V from the analytical model, both models that I just talked about over the finite elements. So if we are less than 1, that's mean the analytical model are predicting less strength than the finite elements, or the analytical model are conservative. If exceeding 1, the analytical model are not conservative. So Cezanne and Molly generally predicted values less than 1. That's mean it's conservative, but the reality is it's actually too conservative. So it was too conservative. On the other side, Kowalski and the Presley model was on the unconservative side. We also look for other models developed for, because those two models were developed for reinforced concrete columns. We looked at also for concrete felt steel tubes. So WashDOT sponsored several research projects. Roders and Lehman and others worked on those projects. And also they developed 2 sets of equations. The upper 3 equations were developed 2012, and then the equation on the bottom were developed more recently, 2016. And again, we here compare this models to the analytical, to the finite elements. So again, both models are unconservative. So looking at those equations, we cannot find really a model that predict quite well the system, which can be understand this is a new system, relatively new system, and those equations were developed, empirically developed for either reinforced concrete or concrete felt steel tube. This is the system that we're talking about here is different. So what we propose here is, as usual, V sub C plus V sub S, but we only use 15% of V sub S. And then we have the, based on the parameters that we investigated, we develop empirical expressions for V sub C and V sub S. Over here, the new equation is a yellowish one over there, so the square. And as you see, the error which is the finite element minus the analytical one over the finite element. So the error for the new one is really the minimum, and it's close to 0. With this, I reach to the conclusion of my talk. We see high hollow core columns can behave very well if it's well designed, similar to reinforced concrete, well-confined reinforced concrete. The concrete wall improve very much the shear strength of the column, and we develop a new equation for the shear capacity. I would like to thank my sponsor and my students. All the folks with the yellow hats are the engineers from MoDOT, and the rest are my research group, and those were my sponsor, and thank you.
Thank you, Professor ElGawady. I am not sure whether our next presenter is here. If not, then we may have some question. Like there is one question asked by one of the attendees. What was your confinement model that you used, if you can share?
I didn't hear the question. What is the question again?
The question was for your numerical analysis. What confinement model did you use?
Okay. I think it was one of the models that developed by Professor Teng group from Hong Kong. Professor Teng group developed a confinement model for hollow core columns or hollow core sections.
We have received another question. The question is why the ultimate strength in specimen 3 is higher than specimen 1? So you mentioned that in specimen 3 you had embedment length problem.
So this one over there?
Yes.
Okay, so, well, I'm just trying to went through this research program has been going on for about 6 years. So I'm just trying to pick different pieces here. So specimen number 3 has a different thickness. So it has a higher thickness compared to for example, specimen number 2. So the thickness of the steel is not the same. This is why we have a higher strength.
Okay, thank you. The other question was, you tested at very large drift, and geometrically, obviously, when you test it, very large drift, the actuator will be coming at an angle, applying the lateral load. Did you have to do any sort of correction for that?
Yeah, we consider we consider that the applied load is not horizontal, so we take a correction. Yes, we apply correction for the measured force from the actuator.
Okay, thank you, Professor ElGawady.